Okay, in this lesson, we are going to pick up where we left off, talking about Lagrange error bound. In the last lesson, we talked about what it is, how to represent it symbolically, and we looked at some examples of how it's used. Let's pick up with some more of these free response examples that we could likely see in the future, and how we can use that Lagrange error bound to solve some of these problems. All right. Example 3 says, let f of x equals sine of x squared plus cosine of x. The graph of y equals absolute value of the fifth derivative of f of x is shown below. All right, so they're giving us a graph. They don't give us any of the other derivatives graphs or any other information about those, but they do give us the function. So in part A, it says write the first four non-zero terms of the Taylor series for sine of x about x equals 0, and write the first four non-zero terms of the Taylor series for sine of x squared about x equals 0. All right, so from previous lesson, sine of x is one of those functions that you need to know the Taylor series for. Sine is an odd function, which kind of helps me remember that we're looking at our odd powers and our odd factorials. So x to the first power over 1 factorial. And it's an alternating series. Next odd power over the next odd factorial plus the next odd power over the next odd factorial. And what does it say? First four non-zeros, so we need to go out one more. So x to the 7th over 7 factorial. We're subtracting that one. So that's sine of x, but we want sine squared of x. So in the previous lesson, we talked about how if we start with our Taylor polynomial for sine of x, now we can just plug in that x squared value. So we should get x squared minus, and then x squared cubed would be x to the 6th power, still over 3 factorial, plus x squared to the 5th, power to a power. We multiply those, so that's x to the 10th, still over 5 factorial, oops, minus x to the 14th over 7 factorial. All right, boom. So there's our sine of x squared Taylor series about x equals 0. Part B says, write the first four non-zero terms of the Taylor series for cosine of x. All right, that's the second part of that original function. Okay, we got our first part there in part A. Probably see where this is going. It says use the series and the series for sine of x squared found in part A to write the first four non-zero terms of the Taylor series for the whole function f. All right, so cosine of x. Remember, cosine is a even function, so we're looking at the even powered terms. The first one is x to the 0, which is just 1. It's also alternating. Next even power is 2. And it also says 4 non-zero terms, so one more, and we're good. All right, so it says take that and what we got in part A and combine those two. So we're going to combine these two functions together, add them up, and that's going to give us our f. All right, so our f of x, which is sine of x squared plus cosine of x. We can approximate that with the sum of these two here. So we've got, if we try to do it in increasing degree order, we've got 1. We've got 2 terms with an x squared in it, so I might combine those two together, x squared and then minus x squared over 2 factorial, which is just 2. And then we've got an x to the 4th term. We've got 2 x to the 6th terms. So I'm going to group those together, simplify that in the next step. 1 x to the 10th. And we've got that negative x to the 14th over 7 factorial from our cosine function. Our sine of x squared function. Okay, so that is our approximation. Let's simplify that a bit. And also it says, let's see, what does it say? Use a series and write the first 4 non-zero terms. So we've got way more than 4 terms there, so we're not going to need all of these. Let's see what we can pare this down to. All right, we still have 1. That's our only constant. X squared minus half of x squared is just half of x squared. And we've got our x to the 4th over 4 factorial, which is 24. All right, so that's 3 terms already. So we really just need 1 more. We simplify that x to the 6th. We're going to get 121 over 720 times x to the 6th. Okay, you can do that fraction simplification on your own. So that is our approximation for our function, first 4 terms of that there. All right, so what are they going to ask us to do with this? Let me highlight that for a moment. We're going to come back to that. Part C says find the value of the 6th derivative of f of 0. Okay, well, if we were looking at that 6th derivative, we would need to look at the term with the x minus 0, or just x to the 6th power, which we've got as our last term right there. All right, so this is our 6th power term. All right, it uses the 6th derivative of our function. So let's take that. And let's say, okay, so that term was 121 over 720 times x to the 6th. Well, that's got to be the same as that 6th derivative 0 over, and then, and then if we were building that polynomial out, that would be divided by that same nth factorial times x to that nth power. All right, so this is going to be what our term is. So let's see if we can solve this for this piece right here. Okay, well, we've got x to the 6th on both sides. If we divide both sides by x to the 6th, those are gone. 6 factorial is 720. So multiply both sides by that 720. Both of those denominators are gone. So it turns out that all we have left is our 6th degree of f at 0 equals 121. All right, part D says let p sub 4 of x be the 4th degree Taylor polynomial for f about x equals 0. Using the information from the graph above, show that the absolute value of p sub 4 of 1/4 minus actual function at 1/4 is less than 1 over 3,000. Okay, so we need to use our graph, use the information above to show that our approximation minus the actual, again, that's our error. Our error is within 1 over 3,000ths of the actual. Okay, or our approximation is within that of the actual. Okay, that's our error. Okay, so let's look at our graph. So we're looking at the interval from 0, which is our center, to that 1/4, which we got from there. Okay, so center 0, so 0 to, let's see, 1 is all the way out there. So each of those hash marks are quarters. So this guy right here is 1/4. Maybe I should write it right there. All right, so we're looking at that interval there. Well, looking at our function, all right, this is that absolute value of the 5th derivative of our function graph. I don't know exactly what that is. It looks like it's somewhere between 20 and 40, somewhere around 30. I don't want to guess, but I can clearly see that it's less than 40. Okay, so this here, all right, we don't know what that equation is for this fifth derivative, absolute value of this fifth derivative. All we got is the graph. So we need to be, essentially we need to be safe, and we need to say we know it's less than 40. All right, so we're going to set our m to be 40. All right, so let's do that. So let's say our error, all right, absolute value of our error is less than or equal to fifth derivative of x over 5 factorial times x to the fifth. All right, because they tell us they want, they're looking at p sub 4, and we were just looking at that fifth derivative absolute value graph. Right, so we said, looking at our graph there, that we feel safe saying that that value is definitely less than 40. You could argue 30, but if that value was 31, then I would feel that would break our accuracy and the truth of our inequality. So keeping it at 40, so we're going to use that value m as 40, or 5 factorial. Actually, let's go ahead and evaluate that. 5 factorial is 120. And plugging in our x, we're evaluating for x equals 1/4. Okay, doing some arithmetic, plugging that into a calculator. That denominator becomes 1 over 3,072. Since that denominator is bigger than 3,000, then that is indeed less than 1 over 3,000, all right, or 1/3000ths, which is what we were asked to show. Boom. All right, example 4. Says the Taylor series about x equals 3 for a certain function f converges to f of x for all x in the interval of convergence, and the absolute value of the fourth derivative of f of x is less than or equal to the fourth derivative of f of 3 for all x over the interval from 3 to 4. Excuse me, the nth derivative of f at x equals 3 is given by that expression there. And f of 3 equals 1/3. All right, A says write the fourth degree Taylor polynomial for f about x equals 3. Wow, okay. So if we were to write our fourth degree Taylor polynomial, okay, what we would need is, and this is about x equals 3, okay, so this is our center. Then we would need f of 3, which we're given right here, is 1/3 as our first term. But then we're going to need each of those derivatives out to the fourth degree to be our coefficients of each of our next terms. Okay, they don't give us that, but they give us essentially a rule to evaluate each of those derivatives evaluated at x equals 3. So we're going to have to do some work and find each of those. So let's do that. So f of 3 we already found is 1/3. All right, the first derivative of f. All right, plugging into that rule. Let's see if I can fit both of them on my screen. All right, and again, I'm just looking at this rule right here. And I'm looking at the first derivative. So my n value is 1. So we've got -1 to the 1 power times 1 factorial over 5 to the first power times 1 plus 3. Okay, if we simplify that, -1 to the 1 is a negative. 1 factorial is just 1, so -1 in the top. And then 5 times 4 is 20. So that first derivative value is negative 120. All right, I'm going to go ahead and find the rest of them, and then we can go in and plug them into our polynomial. All right, second degree. Using the same rule. All right, so this guy here, we're just plugging in our derivative, what nth derivative we're doing. All right, you could even write this as f parentheses 2 if you wanted to kind of jump the gun on what that n value is to make it a little clearer to yourself. I'm okay with either way. All right, plugging in n equals 2. Simplifying, we get 2 over 125. I'm going to go ahead and find the last two. Okay, so once we've found all of those derivatives at x equals 3, now we can take them and plug them into our Taylor polynomial. All right, we've already got our first term, that 1/3. Our next one is going to take that first derivative, divide it by 1 factorial. Again, you don't have to write that. I just like to have it to be reminded of my pattern. We're going to need to simplify this in a next step anyways. So I'll go ahead and put that 1 exponent up there too. All right, next term, that second derivative, which was 2 over 125 over 2 factorial times x minus 3 squared. And the last two terms, that negative 6 over 750 over 3 factorial times x minus 3 cubed. And one more term, taking that last derivative that we found. Where is that? That fourth derivative there. This guy right here. Nope. That was the third derivative. Taking that fourth derivative here. 24 over 4375 over 4 factorial times x minus 3 to the 4th power. All right, let's see what we can do to simplify that. Can't do anything with the 1/3. This is just negative 120 times x minus 3. 2 factorial is just 2, so 2 over 2. That leaves us with just 1 over 125 times x minus 3 squared. 3 factorial is 6, so 6 and 6. This is subtraction though. We still have that 750 in the denominator. X minus 3 cubed. And 4 factorial is 24. So boom, boom. We're left with 1 over 4,375 times x minus 3 to the 4th power. Boom. So there's our 4th degree polynomial for f about x equals 3. Okay, part B says find the radius of convergence of the Taylor series for f about x equals 3. All right, so our general rule, looking at that polynomial that we just got, is that nth derivative at x equals 3 over n factorial times x minus 3 to the n. So if we were looking at that series, Taylor series, that infinite Taylor series, so we would say our sum as n approaches, or n equals infinity to, n equals 0 to infinity, we've got -1 to the n times n factorial over 5 to the n times n plus 3. All right, where do we get that? Well, that we're told was our f of n, or f to the nth derivative of f at 3 back in our original problem. So if we sub that back in, and then we say, okay, so the rest was divided by n factorial times x minus 3 to the n. Okay, what can we do there? Well, we've got a n factorial divided by n factorial. So our sigma from 0 to infinity. It's got that alternator. It's got 5 to the n times n plus 3. And the denominator times x minus 3 to the n power. Okay, so that would be our rule for our Taylor series there. All right, if we were to keep going and find that out to an infinite number of terms, we want to find the radius of convergence, that ROC. So remember, to find that radius of convergence, we typically use the ratio test. All right, almost everything is raised to the nth power here, so we could almost use the root test, but that n plus 3 is not. So we're going to stick with our ratio test. All right, going back to skill from earlier in the unit, we're looking at the limit as n approaches infinity of the absolute value of our next term of our rule. Okay, since we're doing absolute value, we don't need to worry about the alternator. Absolute value, it's not going to change signs, so we can just look at the rest of our rule. So that's that x minus 3. All right, but that next term is going to be to the n plus 1. All right, and that 5 is going to be raised to the n plus 1. That's our next term. And then n plus 1 plus 3 is just n plus 4. All right, I don't have any room to divide, so I'm going to multiply by the reciprocal right away. This is of our current term, or our rule itself. All right, so if you remember using the ratio test, now we're looking to simplify. All right, we want to simplify as much as we can before we evaluate our limit for n approaches infinity. All right, let's group together like terms. Let's go ahead and split up those exponents with sums in them as well. So that first one can be x minus 3 to the n times x minus 3 to the first power. We don't really need to write that. And then I'm going to group that with the other x minus 3 in the denominator. All right, next term on the top is a 5 to the n. In the denominator, let's see, that 5 to the n plus 1, I can write as 5 to the n times 5 to the 1. And what do we have left? The x minus, no, we got the x minus 3, n plus 3. So we've got an n plus 3 in the top and n plus 4 in the bottom. We'll group those together. All right, I think we got everything there. Let's see what we can cross out. We've got x minus 3 to the n, x minus 3 to the n, 5 to the n, 5 to the n. Anything divided by itself is 1, so those go away. So let's see what we have left. All right, let's go ahead and evaluate our limit while we are at it. Okay, so notice that when we're evaluating our limit, we're evaluating as n approaches infinity. So that doesn't affect that x minus 3, and it doesn't affect that 5 in the denominator. All right, freaked out a little bit there. All right, what we do want to do is say, okay, so let's look at this. Looking at our, EBM would just be n over n, which is just 1. All right, so this is essentially times 1. All right, so our ratio, our limit, just be x minus 3 over 5. So remember, for our radius of convergence, we want that ratio between terms to be less than 1. All right, so let's take that. And let's say, all right, so either way, plus or minus, so let's take the absolute value. Excuse me, we want that to be less than 1. So let's solve that inequality. Or do we have space left? We're going to go up. We're going to go down. Let's go down. All right, we're going to write kind of small. All right, so if we drop the absolute value, solve that one, and drop the absolute value, change the sign, we're going to solve that one too. All right, so times 5 on both sides, add 3 to both sides, All right, so we've got our range of 8 and -2. So if we want to find the radius, then we take the difference of those two and cut it in half. All right, so that's going to be 10 over 2. That's going to be 5. All right, so coming back up here, our radius of convergence ends up being 5. All right, part C. All right, last part for this example says, show that the third degree Taylor polynomial approximates f of 4 with an error less than 1 over 4,000. All right, so we know that the center is at 3. And we're going out to 4. Okay, so this is our center. And 4 is the value that we are approximating. All right, we can build our interval from that. And we can say, all right, so our error term, since it says the third degree Taylor polynomial, we want to look for our error. We want to look at the next term. So that's going to be our term with our fourth derivative of f of x over 4 factorial times x minus our center 3 to the 4th power. Okay, looking at previous problem, we've already found f of our 4th degree of f at 3 right here, which was at 24 over 4375. Okay, so let's plug that in. So 24 over 4375 over 4 factorial times plugging in that 4 there. All right, we're looking for f of 4 minus 3 to the 4th power. And let's see what we can do with that. All right, 4 minus 3 is just 1 to the 4th power. It's still just 1. We don't need that. 4 factorial is 24. Those go away. So we're left with 1 over 4,375. We're looking to see if that is an error less than 1 over 4,000. Because the numerators are the same, the denominator is bigger. That means the value is smaller. So it is indeed less than 1 over 4,000. All right, one more example left. Example number 5. It says, let h be a function having derivatives of all orders for x greater than 0. Selected values of h and its first 4 derivatives are indicated in the table to the right. The function h and these 4 derivatives are increasing over the interval from 0 to 3. Okay, so checking out that table, we got a lot of values going on there, from original h of x to the fourth derivative, and x values 1, 2, and 3. Okay, so this is a way that they can ask a question like this without giving you an equation, to kind of see if you understand the concepts of, and kind of apply this to where you don't have an actual equation, but you can, you know how to create a Taylor polynomial, you know how to find the error, and how to find all those coefficients. All right, so part A says, right, first degree Taylor polynomial for h about x equals 2, and use it to approximate h of 1.9. Is this approximation greater than or less than h of 1.9? Explain your reasoning. All right, we've seen problems like this before when we were first learning about Taylor polynomials and how far out they converge and how good of approximation they are. So it says first degree Taylor polynomial. So that is a tangent line every time. All right, first degree, it's just going to be linear. All right, and it's got to hit, it's got to equal the function at that point, and it's got to equal the derivative of the function at that point, that center point. So it's got to be that tangent line. So first degree Taylor polynomial, we want to find what is h of 2. Okay, so h of 2 is 80, and we're going to add to that the derivative of h of 2, 128, times x minus c. Okay, that's that first degree Taylor polynomial. All right, you could put 128 divided by 1 factorial. We don't need to do that. All right, let's simplify. And let's go ahead and plug in our values for x and for c. So first degree Taylor polynomial for 1.9 is 80 plus 128, and the x value is 1.9. Our center is 2. So we're going to get 80 plus 128. That's going to be a negative 0.1. And if we evaluate that, we're going to get the value of 67.2 as our approximation. Okay, so that is our approximation of h. So h of 1.9 is approximately p sub 1 of 1.9, which is 67.2. All right, then in the second part, they say, is this approximation greater than or less than h of 1.9? We don't have a graph. We don't have an equation that we can put into our calculator. So we're going to have to rely on our second derivative test to look at concavity. It does say that our function is, what does it say, increasing over that interval. Okay, so we know it's getting bigger. If we can show that it's concave up, then we can show that we've got an underestimate. So second derivative, let's come over here, h double prime, all right, at that center, h double prime at that center is positive, all right? It doesn't actually matter what that value is. All these values are positive. So that 488 over 3 is indeed positive. So 67.2 is an underestimate. And let's give our reason. Since we just saw that h prime double prime of 2 is positive. All right, and again, the visual that goes along with this, we've got a graph. Let's say this is our original. We're looking at our x value of 2. Then our let's label this. Let's make sure this is my h. Then the first degree polynomial that we just found, that tangent line, is going to look something like this. Okay, that's my p sub 1. All right, so if it approximates 1.9, all right, at x values of 1.9, and that approximation is going to be somewhere around there. That's going to be less than what the actual is. All right, it's going to be an underestimate. All right, again, we know that's an okay sketch for h because we know it's increasing over this domain from 1 to 3, and the second derivative test told us that the second derivative was positive, so it's concave up. All right, so part B. A few more to go. Write the third degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. All right, so third degree Taylor polynomial. We already know our first two terms, 80 and plus 128 times x minus that center. All right, so let's find the next two. So we're going to take the x value, that's second degree of h, divided by 2 factorial times x minus c squared. And then for our last term, since we only need to go to our third degree, we're going to go out to our third derivative of h at 2. All right, we're still looking at our center of h, c equals 2. All right, for 48 over 3. And that's over 3 factorial times x minus c to the third power. All right, so simplify that a little bit. Let's see, 40 over 2, that's going to be 2. 44 over 3 times x minus c squared plus, and then if we simplify that last term, we can simplify that to 224 over 9 times x minus c cubed. All right, so that is our piece of 3, our third degree Taylor polynomial. We want to use it to approximate h of 1.9. All right, so we can say h of 1.9, our new approximation is using our, what do we call this, piece of 3? Oops. At 1.9. All right, and if we were to plug that into each of those x's and evaluate in our calculator, we would get 67.988. And boom, that's all they asked us to do. All right, so compare that with what we got for our first degree Taylor polynomial. And that's going to be a better approximation. All right, so it's looking like it's getting closer to 68. All right, part C says, and this is it, last one, people. Use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative fourth. All right, so what is that? 10 to the negative fourth, if we do scientific notation, it's going to be 0.0003. All right, so we want to find error less than that. So our error is going to be less than or equal to, and it says we're looking at our third degree Taylor polynomial still for that last one, just like we did in that last one. So we need to essentially find that next term. All right, so that following term. So again, that is our going to be our fourth derivative of f at x. All right, looking for our Lagrange error over 4 factorial times x minus, our center is still 2 to the fourth power. All right, and you'll notice in the different kind of forms of these terms, the absolute value can be in different places. Sometimes it'll be with this numerator here. Sometimes it'll be around the x minus the center. Not a big deal. As long as we're looking at that value of the error, not negative, then several of those are equivalent to each other. All right, so plugging in those values. That next term, looking at our table again. Looking at our table one more time. Still at center of 2. We actually, turns out we didn't need either of those other rows, just when our center was 2. Fourth derivative, 584 over 9 over 4 factorial times our x value. They say we're evaluating 1.9 again to the 4th power. All right, we're looking at the absolute value of that, which all those are positive anyways. This raised to the even power is going to be positive. We can put it in absolute values anyways, doesn't matter. All right, putting that in your calculator, we're getting 0.00027. So that's 27, what is that, tens, hundreds, thousands, 10 thousandths, 100 thousandths. That's 27 hundred thousandths of a unit of error. And that is indeed less than that 3 times 10 to the negative 4th, or 0.0003. Again, depending on your application, that looks super accurate to me. That's a small amount of error, but it depends on what kind of numbers you're dealing with, what your application is, if you were actually using this in a problem. All right, so several good examples of some FRQs for how Lagrange error bound can be used. Make sure you try those practice problems, homework problems on your own, and come with questions to the next time we meet.